Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on PlumeStop longevity for in-situ PFAS plume treatment. With that, I'd like to introduce our presenters for today. We're pleased to have with us Dr. Grant Carey, President of Pore Water Solutions. Dr. Carey is an expert in mathematical modeling, NAPL characterization, and environmental forensics, with a focus on both litigation and regulatory projects across the United States and Canada. He has a PhD in environmental engineering and has developed industry-leading modeling and visualization software. Dr. Carey is also an adjunct professor in the Department of Civil and Environmental Engineering at Carleton University, where he is collaborating on research related to PFAS, fate and transport, and in-situ remediation. We're also pleased to have with us today Ryan Moore, PFAS Program Manager at Regenesis. Ryan has 20 years of experience as an environmental project manager and laboratory account executive relating to multimedia contamination sites throughout the US. His experience has focused on site investigations of soil and groundwater contamination, corrective action evaluations, operation and maintenance of remediation systems, large soil removal remedial projects, and in-situ groundwater and soil treatment. All right, that concludes our introduction. So now I will hand things over to Grant Carey to get us started.
Thanks, Dane, and hello, everyone. I appreciate everybody coming out today and making time to join us. Thanks very much. So I'm assuming that most people online today are very familiar with the widespread problem we have with PFAS contamination in groundwater and the real challenges we have with in-situ remediation of these PFAS plumes. One option that's gained a lot of interest these days is injecting colloidal activated carbon. These are small particles of activated carbon. Regenesis sells this as PlumeStop. We can inject this PlumeStop or CAC into aquifers through temporary injection wells, for example, right in the PFAS plume. And then over time, these little particles of activated carbon will actually move some distance away from the wells, not a lot of distance, but some distance, where they'll basically attach to sand and gravel grains that are in the porous media, and they'll stay there. And the PFAS plume, as it moves through the CAC zone, will absorb very strongly to the colloidal activated carbon. So there's a real benefit for reducing mass flux from these plumes using activated carbon with solutions like PlumeStop. So today I'm going to talk first quite briefly about some basic PFAS concepts and also colloidal activated carbon concepts. And then I'm going to review a PFAS case study was done at a site in Canada by Rick McGregor at In-Situ Remediation Services Limited. This is a site where PlumeStop, colloidal activated carbon, was injected into the aquifer. And very quickly, we saw that the PFAS constituents were reduced to below detection limits within a matter of months. And they've been below detection limits now for 4 years and counting. So we'll look at that study, and that's a site where PFAS and PFOA had maximum concentrations of up to 1 to 3 part per billion microgram per liter. So one question we've had is, okay, how long will colloidal activated carbon work at sites where we've got higher PFAS and PFOA concentrations, more in the 10 plus microgram per liter range, like we see at AFFF sites? So to help with that, I'm going to walk through an example, a groundwater plume for PFAS constituents at an AFFF site to tell us what typical concentrations might look like. And then also we've partnered with the University of Waterloo. Dr. Ryan Pham has developed some absorption isotherms, which allow us to quantify how much PFAS will absorb the colloidal activated carbon. Um, so we're using those absorption isotherms to then model the sensitivity of the longevity of this remedy to things like what if we have lower concentrations or higher concentrations or lower high velocity? What are the site characteristics that really affect the longevity of a remedy like PlumeStop at PFAS sites? So for the introduction, I'm again assuming that most people here have a general understanding of PFAS. So I'm going to do us all a really big favor and not mention all these really long, complicated chemical names, just to shorten this presentation up. So the image we're looking at is a PFAS molecule. PFAS is one of the most common contaminants we hear about when we think about PFAS in groundwater. And a key characteristic here of a PFAS molecule is it's got 8 carbon atoms that are joined together in this chain, basically the tail of the molecule. So it's an 8-chain carbon molecule. It's also got these fluorine atoms in green connected to the carbon atoms, which are in blue. And those carbon fluorine atoms are the strongest we'll find in nature. And that's why molecules like PFAS are very, very difficult to degrade. They really were engineered to be robust, which means they're very persistent in the environment, which is one of the challenges we have with in-situ remediation. So looking at these tables, these are typical constituents, PFAS chemical names that we see in sites contaminated by PFAS. PFAS we've talked about, that's got 8 carbons. We've also got PFOA, another common 8-carbon PFAS constituent you hear about. And as you go down this table, the number of carbon atoms actually decreases, and these chains of carbon atoms get smaller and smaller. So the key thing to know is that the chemical names shown here in blue with the yellow highlighting, those are defined as long chain PFAS. These are the ones that are typically of most regulatory concern because they have the high absorption inside our bodies. They bioaccumulate more than the short chain PFAS, and that makes them of more concern, higher risk. So that's why we tend to focus on these longer chain compounds during groundwater investigations and cleanups. So if you want more information on PFAS, I would definitely strongly recommend you check out the new ITRC PFAS guidance manual. It's a web-based document. You can see the website listing up here. I've been on the ITRC team for about 3 years now. One thing I contributed, which I'm quite proud of, are these the use of radial diagrams. And this presentation isn't about radial diagrams, but if you're interested, these are very helpful because there are so many PFAS constituents we need to look at and evaluate trends, upgradient, downgrading along groundwater flow paths, see whether biodegradation is occurring. These are helpful for a number of reasons. So if you're interested, there is a tool on our website called Visual Bio. It's a free tool to download. It's a little bit cumbersome. We are coming up with a Windows version for next year. But just in case you're interested, that is something that you may want to check out. So with PFAS, there are different types of PFAS sites. Some sites like landfills and wastewater treatment plants have fairly low concentrations of PFAS constituents and plumes, more in the nanogram per liter range. Other sites, especially like fire training sites where aqueous film forming foams were used historically, those can have higher concentrations of PFAS in groundwater in the tens to hundreds of microgram per liter at some sites. And the range of concentrations is important because the lower the concentration in a groundwater plume, the longer a colloidal activated remedy will work with a PFAS plume. So some sites, like especially the lower concentration plumes, longevity is fairly high. Even the higher concentration plumes, we can engineer these remedies to have higher longevity, and that's something we'll discuss with modeling a little bit later. So one thing I wanted to point out is using activated carbon to treat PFAS is not new at all. We've been using this for a number of years with ex-situ groundwater treatment. We've been using granular activated carbon because it's very effective at removing PFAS from groundwater. Granular activated carbon particles are quite large. These are to scale. Powdered activated carbons are smaller, more in the 25 to 100 micron range. Colloidal activated carbons are even smaller, much smaller actually, 1 to 2 microns. And the real advantage of these small colloidal-sized particles is because they're so small, they're really easy to inject into aquifers. They don't clog pore spaces. They can go into finer sands quite easily, even at low pressures. So we don't have to fracture soils to get the colloidal-sized particles into the aquifer, which means we don't get preferential distribution, and they're more uniformly distributed because of their small size, which is a real advantage. Another advantage, in addition to the small size, is the absorption strength actually increases as you decrease the size of these activated carbon particles. So to show this, the yellow symbols here are from a groundbreaking paper by Jiao et al. Dr. Chris Higgins was a co-author on this paper. They looked at how, as the activated carbon particle size decreases from left to right on this chart, the absorption strength actually increases. And based on a sample data I'd received from Regenesis a few years ago, I plotted an effective KD up here for colloidal activated carbon. So it's even higher absorption strength per gram of carbon than powdered activated carbon. So that's a second advantage. It's quite different from granular activated carbon for that reason. So in terms of applications, the photograph on the left, provided by Rick McGregor of In-Situ Remediation Services, shows what a PlumeStop slurry looks like before it's injected into the ground. So this has these small, tiny little particles of activated carbon. It's got a polymer in it that helps to improve the distribution, so it's more uniformly distributed. The activated carbon particles don't conglomerate together. And typical radius of influence might be something like 10 feet. That's a site that the case study I'm going to talk about had that measured as a radius of influence. And the picture on the left I find really effective for visualizing how these activated carbon particles get distributed after injection. This photograph was provided by Regenesis, and you can see the large particle in the photograph is one sand grain. And these small little particles on the surface that are attached to that surface, those are the colloidal activated carbon particles, about 1 to 2 microns in size. And so after injection, like any colloid, if we inject zero valent iron, if we inject emulsified oil, these are colloids. They do move a little bit away from the injection well, and eventually they attach to the sand grains in the aquifer. And activated carbon is the same way. So that's what it looks like, these small little particles of activated carbon attached to the sand. And then as PFAS or other contaminants move with groundwater flow through the porous media, they basically absorb to these carbon particles very effectively. So in terms of what a retardation coefficient looks like with activated carbon, this is a really conceptual plot. So let's say we've got a groundwater plume with PFAS at maybe 10 microgram per liter. That might fall somewhere like here on the chart. Before the carbon's injected, we've got 10 microgram per liter PFAS. After carbon's injected, the concentration of PFAS goes down substantially, usually below detection limits. So it might be here on this plot. And at these really low concentrations, we've got very high retardation coefficients. Now over time, as the plume continues to move through that CAC zone, we've got more mass coming through. The absorption sites get filled up a little bit more over time and more. So groundwater concentration increases a little bit, the retardation coefficient declines. Eventually those absorption sites will get saturated and will return back to the original groundwater concentrations. And we'll talk a little bit later about things we can do to actually account for that with remediation at sites. So next, let's turn to a case study. This is, I think, the first site I've ever seen where PFAS were actually treated in situ. This is a site that Rick McGregor worked on. It's a site actually in Canada. So where initially, Rick actually gave a seminar for Regenesis about the site about 2 months ago, and he called it the accidental site because it really was a petroleum hydrocarbon site. He had heard before remediation that they might have actually had fire training in a small area at this site. So he did an investigation for a sample for PFAS and PFOA. And sure enough, he actually had some low-level concentrations, 1 to 3 microgram per liter PFAS and PFOA at this site. You can see generally the source area is where that black line is delineated. So he, as part of this site, he injected PlumeStop, and he injected also substrate to enhance aerobic degradation or degradation of the petroleum hydrocarbons. But sure enough, the PlumeStop, the colloidal activated carbon, also completely attenuated the PFAS at this site. So after the injection, when he went back 3 or 6 months later to do the first round of monitoring, the PFAS and PFOA were non-detect everywhere. So it was clearly quite effective for also attenuating the PFAS. So about 3 years ago, I had worked with Rick. I got the data from Rick for this site and actually developed a model so we could simulate what happens when the CAC, the colloidal activated carbon, was injected. So around that source area, and also where there was co-located petroleum hydrocarbons, Rick had done injection of PlumeStop, colloidal activated carbon, basically around this blue area. That's the outer perimeter of where the temporary injection wells were. In this part of the site, where there was PFAS also, there were about 20 to 30 injection wells spaced about 10 feet apart within this blue zone that we see. And there was another area where there weren't any PFAS, so I'm not going to show that part as part of this presentation. So what happens was, and we're seeing model results here that show that 6 months after that injection, I've got a model that actually simulates, okay, when the carbon's injected, it represents what happens, how the PFAS basically absorb to that carbon after it's attached to the sand grains in the aquifer. So this shows 6 months after we've got plume detachment, where the source in this area, the source is still turned on in the model, but the model shows that with the carbon injected, it's basically preferentially absorbing that PFAS and preventing it from moving down gradient. And that's where we see that plume detachment occurring. So just using radial diagrams, just to show not just PFAS and PFOA, within about 18 months, Rick was measuring all the PFAS constituents you typically get in labs, 20 to 30 constituents. And this just shows some of the sulfonates and one precursor that were measured. And the symbols here, the white symbols, are all mean non-detects. So in 2017, which is this blue data series, we had low concentrations at all the wells. There was one well that had one minor detection of PFAS at about 30 or 40 microgram per liter. With multiple events after this one, it was never detected again. So the thinking is this may have just been cross-contamination in the field or from the lab. And you can see the original pre-injection concentration for PFAS at this well, 1,000 nanogram per liter. After the injection, it had dropped by 1.5 orders of magnitude. And looking at all the other wells in the CAC zone, we see the same thing, drops of 1.5 to 2 orders of magnitude. For PFAS, we only had PFAS before the injection, but you can see after the injection, we didn't see any of the other constituents. And 4 years in now with monitoring at the site over 4 years, we're still at non-detect levels. So clearly at the lower concentrations, PlumeStop works well because it's absorbing these PFAS and preventing it from moving down gradient. Just to show what it looks like longer term, I had published a paper with Rick and other co-authors in the Remediation Journal last year. So if anybody's interested, just send me a quick email. I'm happy to send that paper to you. So in that paper, I looked at simulating, okay, a longer term, using absorption parameters that were developed by Dr. Ryan Pham and Seyfola Hakimabidid. They both worked hard in the lab to develop these isotherms that allow us to quantify longevity in the longer term. And you can see in the first year, we're not seeing PFAS, it's below detection limits. After 10 years in the source area, we do have PFAS at about 0.1 microgram per liter because that source is still on in the model. I'm assuming it's back diffusion or some kind of source that's continuing the flux. So over time, those colloidal activated carbons do start, the absorption sites get filled up, the concentrations increase. It's another 3 or 4 decades before that plume is going to basically break through that CAC zone. So because we have a fairly long CAC zone here, we can see that these PFAS really get attenuated for a long period of time. So we talked about a site where PFAS and PFOA were at concentrations, maximum numbers of 1 to 3 microgram per liter, which leads to the question, how long will colloidal activated carbon or PlumeStop work at sites where PFAS are at higher concentrations, like we find at AFFF sites where concentrations can be as high as tens to hundreds of microgram per liter? So to help with that, I've gone into the literature, there's one site that's really well documented, and I'm going to use that as an example of a PFAS plume at an AFFF site that we'll then go and model a little bit later to see how longevity works with this kind of site. So I like this photograph because it shows the former fire training area, this uncovered depression here in the ground that was used up until about 1990. And then you've got the new fire training area installed in about 1990 with concrete liners. So clearly nothing's getting through there. So these AFFF sites, what we're really dealing with are sites where typically these are sites with older plumes, older sources is the most common type of site that I've seen. So there's a great paper by Megan McGuire, who's a former grad student of Dr. Chris Higgins at Colorado School of Mines. And in this paper from 2014, she went through a summary of what the groundwater plumes look like at this particular Air Force base for data that had been collected in 2011. And she's got more information in the supporting info section and in her master's thesis. But there has actually been more recent monitoring since, and there's been new groundwater samples at new locations collected since then. So what I did is I combined the data that Megan had collected with more recent data, which was available online. I haven't worked on this site. These are basically just publicly available data that I've looked at. And putting it all together, this is what the PFAS plume looks like. There are a couple of small source zone areas up to the east and the north, and that's why this plume is a little bit wider than what you might expect with just a former fire training area as a source. There is a couple of characteristics of this that are important and are actually consistent with other PFAS like PFHXS and PFOA. One is the highest concentrations are right here near the former fire training area, where concentrations are over 100 microgram per liter. And as you go down gradient, there is a narrow, fairly long core of the plume where concentrations are over 10 part per billion, between 10 and 100. And they do decrease with distance down gradient from that source area. As you'd expect with dispersion and mixing, you do expect that to happen. So what I did is I looked at, and I'm not showing the other two plumes, PFHXS and PFOA. Those are the other two commonly detected long-chain PFAS compounds at AFFF sites. Because PFAS is pretty similar, so there was no need to show all three plumes. And what I wanted to do was try and find what's the maximum concentration along a transect, some distance down gradient from the source area in this plume. And the maximum concentrations are important because our longevity is really driven by where concentrations and flux are going to be the highest across the width of that plume. I also wanted to go down gradient, some distance down gradient, for two reasons. One is when you're actually in the source area, there are compounds present that we call precursors. They're larger molecules. They may actually interfere with absorption of these target compounds to the activated carbon that we're injecting. So you don't really want to inject activated carbon in a AFFF source zone. There's other molecules that might interfere, limit the absorption. If you go down gradient, you're going to have less competitive interference. And you've also got lower concentrations of these target compounds when you're down gradient of the source zone. And what I'm going to show later with modeling is the lower the concentration in the plume, the greater the longevity is going to be for a PlumeStop or colloidal activated carbon remedy. And one other thing to consider too is that if you can actually decrease the mass flux or the concentrations in the plume with other alternatives that you're combining with PlumeStop. For example, if you're getting a lot of mass coming from the vadose zone down to the water table, maybe for PFHXS, which doesn't absorb as much as PFAS does. If you're still getting a lot of mass coming from the vadose zone to the water table, if you pave over that uncovered ground surface, you can reduce the flux getting into the plume, and that ultimately reduces the down gradient concentrations, giving you greater longevity for your PlumeStop remedy. So that's something to consider as a combined alternative if the cost benefit warrants that. Okay, so we've got the concentrations, and next we wanted to look at, we had to quantify what the absorption isotherms look like so we could actually model longevity. So I've worked with the University of Waterloo to do this, and to help with that, we wanted to get a groundwater sample from an AFFF site so we could get representative absorption isotherms. So Dr. Charles Schaefer provided this groundwater sample, concentrations of this sample are actually higher than the representative plume we saw. These might be closer to a source zone. You'll see precursor concentrations are actually over 70 microgram per liter, and there's pretty high dissolved organic carbon, about 24 milligram per liter. And that dissolved organic carbon and the precursors may actually interfere with absorption of our target PFAS. So these absorption isotherms may actually be conservative if we're able to go further down gradient in the plume where there's less carbon, less organic carbon, and less precursors. So Dr. Ryan Pham, and specifically Saifola Hakimabadi is a PhD candidate working with Dr. Pham. Saifola spent countless hours in the lab developing these isotherms. It's tricky working with these low concentration PFAS solutions with carbon in them. He's done a great job at showing, first of all, developing isotherms, and I've got retardation coefficients plotted here, for example, where we just have PFHXS in the water. And that single species isotherm and retardation coefficient is about 100 times higher than what we get with a groundwater sample where we've got precursors mixed in and organic carbon. So that's showing that if you want to get a more representative picture of longevity, we've really got to do site-specific isotherms with groundwater samples from a site where you've got these other chemicals present, so we can actually look at competitive effects with these absorption isotherms. So next, now that we've got the concentrations in the plume, we've got the absorption isotherms, now we've got what we need to actually model the longevity for different conditions. So the base case scenario is using those plume concentrations that we talked about earlier for the 3 long chain compounds most of interest at AFFF sites. I set up a simple one-dimensional model, about 1,000 feet long. I've got a CAC zone where I simulated a fraction of colloidal activated carbon, a range of numbers here, 0.02% to 0.08%. These are numbers that Rick McGregor has measured at sites. So that gives us a measured range of what we're using in the sensitivity analysis. And I varied the length of this. Typically it was 40 feet. I also modeled 80 feet to see what difference that would make in the length of the longevity of the remedy. And velocity, base case is 55 feet per year, about average for contaminated groundwater sites. And I've got the low number is that average divided by 3, and the high number is that average multiplied by 3. And then finally, I looked at a range of concentrations as well to see how those affect the longevity of the remedy. I'm going to skip past the slide just for time. There are some things in this transport model that I've developed that allow us to be able to do this. This is explained in that paper I talked about from last year. So if you're interested in more details, I'm happy to send you that paper. So you're looking at the base case, a groundwater velocity about 55 feet per year in the aquifer. With our starting concentrations in the plume, PFHXS, PFOA, and PFOS, the heights of these bar charts represent the longevity for different scenarios. And we can see that PFHXS is the one constituent that has the shortest longevity out of these 3 compounds. And that's partly because it's got a fairly high concentration compared to PFOA. And it's also got a smaller absorption capacity. Carbon's got a smaller absorption capacity for PFHXS and PFOA than it does for PFOS. I found through modeling that PFOS, even at higher concentrations, because it has absorbs more strongly to activated carbon than the other compounds, this one is not going to be your limiting factor, PFOS, with longevity. It's really the PFOA or PFHXS, depending on their plume concentrations. What we do see is using the low end of the fraction of colloidal activated carbon, 0.02%, that's the blue bar, we still get a longevity of about 30 years for PFHXS when the velocity is 55 feet per year. If we increase that colloidal activated carbon fraction by a factor of 4, the longevity increases by a factor of 4 also. So it's directly related. If you double your fraction of carbon in the soil, you double your longevity. So that's really important because we can engineer these sites to have greater longevity by using higher carbon concentrations in the solution we're injecting. And Regenesis can talk to you more about that as well. So in terms of velocity, also a fairly simple ratio. If you divide the velocity, if you increase velocity by a factor of 2, you divide the longevity by a factor of 2. So they're directly related. So what this shows us is 2 things. One is if you've got sites with relatively low groundwater velocity, even with a lower fraction of colloidal activated carbon, you've still got pretty good longevity. Higher fraction of carbon, even better longevity, and velocity is less of an issue for PFH excess in this particular plume we're looking at. So if you've got sites with higher velocity, then you definitely want to make sure you're getting higher fraction of colloidal activated carbon injected. The other thing it shows us is if you have an aquifer maybe with layers with different permeability, one layer's got a higher velocity than the other in one CAC zone, it's that higher permeability layer that's going to be limiting for your longevity if it's thick enough. If it's 1 or 2 inches thick, and if it's got low PFAS concentrations, it's really not going to be a concern for longevity. But I do recommend high resolution characterization where you're looking to actually consider CAC injection. And last thing we looked at was concentration effects on longevity. What this shows is when you've got lower concentrations on the x-axis, like in the single-digit microgram per liter range, you've got very high longevity for all these three constituents. So if you've got a plume with lower concentrations, longevity is not an issue. If you have higher concentrations, you're going to want to try and get that fraction of colloidal activated carbon up. I did find, I didn't show it here, but if you increase the length of your CAC zone, say you double it, then you're doubling your longevity as well. So that's another thing we can do, even where groundwater velocity is higher for some of these compounds, if that's an issue. So we can engineer the solution to try and match the conditions at your site. And uncertainty with modeling, you have to consider where the uncertainty comes in. There are some factors we didn't include in the model that if we had included them, would have actually increased the longevity. I won't go into the details of these, but there are some factors here that make me think these isotherms are conservative. There are a couple factors that if we considered, longevity would have been decreased by some amount. Competitive effects, we do have those in our groundwater mixture isotherms to some degree. I'm not sure what the effects are over time. I'm actually working with a couple of university teams to look at this in more detail. And then the short chain PFAS, if they are risk drivers or regulatory concern at a site, we need to be able to have isotherms to develop, to be able to predict longevity for the short chain PFAS as well. So the last slide, I just want to leave you with the fact that there are, there's some sites where there may be a question about longevity. No question that colloidal activated carbon works. The real question is how long will it work for? What can we do to improve longevity? Regenesis has a lot of those answers. We are looking at a couple things with some university research that's continuing. And I'd be happy to talk to anybody more about that if you're interested. So on that note, I'm going to pass it over to Ryan Moore, who's PFAS Program Manager with Regenesis.
Thank you. This is Ryan Moore, Program Manager, PFAS Program Manager for Regenesis. Today, I'm just going to kind of supplement some information that Dr. Carey provided here previously in the webinar and just kind of go over a few things related to the colloidal activated carbon. Brief overview of the different items I'm going to talk about, just briefly discuss a little bit about the PFAS challenges we see in groundwater plumes, a little bit more on PlumeStop itself, spend most of my time on considerations for using PlumeStop, and then also provide an update for the Camp Grayling field case study that we've been working on for the last couple of years. So the PFAS challenges, primarily when dealing with a lot of these project sites that we're looking at, they're large dilute plumes with plumes that could go under multiple city municipalities, definitely multiple property owners, adjacent to multiple sensitive receptors such as surface body waters, creeks and rivers or lakes, and then even coming across into people's drinking water supply wells. For most of the projects that we're looking at as well, we'll have extremely low target remedial goals. Most cases in the single digits parts per trillion or nanograms per liter type levels. These compounds are extremely difficult to work with. There's very limited destructive technology that's out there, let alone from an in-situ look at it. And the accepted remedial strategy for many of these long plumes is a pump and treat with absorption through using GAC or ion exchange. And pump and treat just does not line up well for these kind of large dilute plumes. You know, Dr. Carey gave a great description of colloidal activated carbon and PlumeStop, so I'm not going to get in too much here, but just kind of want to highlight a few things. You know, we're talking about carbon particles the size of red blood cells, very, very small. It's suspended in that polymer solution that allows the distribution under low pressure. That is very important. And then, as you saw too, is it's extremely fast absorption in relationship to these PFAS plumes. In essence, we're trying to convert the aquifer into a purifying filter. How do we do that though? You know, not just for PFAS projects, but for any project where we're using PlumeStop on, the primary goal is to coat the contaminant flux zones. And by doing that, we're mitigating the migration of the contaminants down gradient. And then we're also preventing against long-term back diffusion under the low permeable areas adjacent to the flux zones. When we do this and we do it correctly, then we can protect sensitive receptors. And again, you know, this is a kind of a look of how we're doing this most often is installing some type of cutoff barrier, permeable reactive barrier. So why PlumeStop? Again, I already talked about this a little bit, but there are limited destruction technologies. One of the big things too is low cost. This is easily deployable in the field. There's no long-term O&M costs. We're not generating waste or, you know, something that has to be discharged and treated. Reapplication will happen after many years or in some cases decades. And it's a fraction of the cost compared to pump and treat in terms of the size of the plumes we can treat. We're also localizing the contaminants. So, you know, we can deploy the PFAS barrier or the PlumeStop barrier, collect the PFAS over time, and then maybe in the future that could be paired with future kind of like destructive technologies to address it. And the PFAS are all in one area where you put that colloidal activated carbon barrier. Biggest thing is we're preventing the PFAS migration. We're removing the exposures and eliminating the risk. So some considerations when using PlumeStop. Dr. Carey talked about this a little bit, but we have to understand what makes up the target compounds we're trying to address. And for PFAS, a lot of times it's kind of breaking up between long chain and short chains. So we have to have a really good understanding of that. We need to understand the groundwater velocity or the contaminant flux through any particular treatment zone we're trying to target. Non-target compounds. This is a big thing, and a lot of times this drives our dose designs more so than the actual target compound. So if we're trying to treat a dilute plume with, you know, 10 nanograms per liter PFAS, but you've got a benzene fluxing in at, you know, 1 part per billion, the benzene is probably going to drive the dosage more than the PFAS would itself. So we have to have a really good understanding for this. Anything that has an affinity to the carbon will exhibit a demand. And then from an application standpoint, we need to really understand your project site. We have a step that we call design verification testing. In essence, what we're just trying to understand, are there any potential data gaps or holes from the site conceptual model that would allow us or to prevent us from building that underground fence, so to speak. So Dr. Carey talked a lot about the modeling that his team is doing. I want to kind of just give a little bit of information here about what we do from internally on our design process. And we have a model we call Plume Force, and it's kind of a fate and transport model where we input different parameters and try to predict what the longevity may be and try to optimize the dose based upon the site requirements or the project requirements. And what I'm going to show you is just kind of a graphical representation of the output from this model. And from left to right, you have it's just basically distance through the plume. You got contamination coming in at different levels. For this graph, you have, you know, PCE at 10,000 nanograms per liter, and then you have some PFAS down here at the lower levels. Groundwater is moving from left to right here. And the goal of any PlumeStop barrier is to install the PlumeStop, and then have the target contaminants be pulled out of the groundwater within this barrier. So a lot of the inputs that we're looking at or collecting from a site-specific basis is, the soil type from the treatment interval, the groundwater seepage velocity, vertical variations. Is this a fine sand coarsening to a coarse gravel? We have to understand that. Are there clays in the mix? Not many sites are similar from top to bottom within our treatment zone. The understanding the application in terms of where we're going to have the placement. Is the barrier a single line injection? Is it multiple line, multiple rows of injection? Is it multiple barriers? Is it more of a grid layout? So we really need to understand this, because then that goes into what the longevity may be. Again, the carbon demand, and then time. What are the requirements that we need to achieve the goals for the site? Some sites might be, say 5 years of retention time. Others might be, 20 years. What does it need to be at, and then how do we optimize that? So going into the update of the Camp Grayling Army Airfield case study, this project site is located in northern Lower Peninsula, Michigan at Camp Grayling. And we were actually working in what they call the former bulk storage area. The bulk storage area, you can kind of see in this blow up, is where they had a series of tanks, and this area where they would offload different equipment, tanks, jeeps, etc. here at the airfield, and they would do maintenance and fueling and their fueling operations. And so the geology here at this area is mostly a sand with some gravel. There's some different clay layers with depth. Groundwater velocity was around 250 feet a year. And then we were targeting for the field test the upper aquifer, the 15 to 27 feet below surface. The contaminant levels, again, this was a commingled plume, so we had PCE in the area at 10 part per billion, and then about 130 total nanograms per liter of total PFAS, and it consisted mostly of the PFOS and PFHXS. The reason why we were looking out here is that there was multiple sensor receptors here. This was right up along the property line of the airfield. There were residential neighborhoods with drinking water supply wells nearby. And then there was the Au Sable River and then a nearby lake as well, where they were worried about PFAS showing up into those water bodies. So Camp Grayling, what we wanted to do is kind of test a simple plume cutoff barrier. And this is just a cartoon to kind of, or an illustration that shows what this is. And so we had one single well that we were going to apply around, and then we had an upgradient wells and then downgradient wells. And then there's a series of injection points where we could, inject the PlumeStop and then refine or optimize the approach in our injection to get uniform distribution in the field. This is just what it looked like out at the actual site. You kind of see the pink flags. This is the arc fashion, and then the upgradient and the downgradient paired wells. One note that these wells were 5-foot screens at different intervals, and so we had to we kind of understand what's fluxing in at different treatment intervals vertically. And this is kind of what it looked like. So when we go out and do one of these injections, we don't just start taking injection points and start pushing it in the ground as fast as we can. We kind of start with the edges and then work our way into the center, or maybe we start in one section and kind of work our way around the arc. But then we also do what we call searcher cores, and then to try to identify visually the radius of influence of the application. And so in this illustration, the orange diamonds are the injection points, and then the yellow squares are the searcher core locations. And what that looked like in the field, just kind of orientate yourself here. The top right is the 0 feet mark, the bottom left is the 30-foot mark. And then our injection interval is basically 15 to 27 feet. And you can see at 27 feet, there's that clay layer, and then the groundwater started right there at 15 to 16 feet. And when we do these cores, it's very obvious when you have distribution. It turns the soil a black color, and that's that kind of painting effect that we have with the PlumeStop. And so when out in the field, and looking at these, each one of the black squares now, we were able to visually identify and verify that we had PlumeStop distributed through the treatment interval. So back to the original goal or intent of any PlumeStop project is, did we coat the contaminant flux zone? And as we were shown here in these cores, we did. So on to the data. I'm going to explain this graph a little bit. The red lines up here at the top, these will be the up gradient locations, and then the green lines are the down gradient locations. I'm just going to talk about the first set of paired wells here, the 29, 29C, 29D, and 29E. These were the original wells put in for the pilot test. And after you see 2 months here data, immediate dose response right down to non-detect. And then after about 6 months, those wells had maintained non-detect while the up gradient kind of bounced around a little bit. So we wanted to kind of maximize the benefit of this pilot test. So the decision was made, well, let's look even farther down gradient. And so what I'm showing you here now is just, it's kind of busy, but what I want to kind of bring up are we put in a couple additional paired wells, one at 26 feet and then one at 45 feet. We also put in some wells out here on the edges just to kind of refine the groundwater direction a little bit better. We knew overall that it was going, pretty much one direction, but we started this off with one well out in the middle of a field, and so we're kind of refining that a little bit. And it was a good thing we did, because groundwater actually came into this pilot arc as at an angle. So on to the continuation of the data. And so as you can see, through 600 days, all the way through 45 feet down gradient, we're non-detect, and we've been non-detect through that 600 days. When we first put in the wells that were 45 feet, we had detections that were near or slightly above the detection limit, but since then, as additional sampling has occurred, everything's been maintained non-detect down gradient of the application area. I did mention that this was a commingled PCE plume. Again, this is the PCE data. Notice the scale is a little different. This is micrograms per liter versus nanograms. The PCE kind of fluxed in to the treatment area. It's pretty consistent over time. Just like in the PFAS, the 2 near downgradient wells, immediate dose response, and then went to non-detect, maintained non-detect ever since. At the 26 feet and 45 feet down gradient, what's interesting is at 45 feet, we still had some PCE above the detection limit, but as we've continued to sample, that has too come down, and that kind of matches up with our prediction on the models that as you move away from the barrier, it just takes longer to see or realize those same reductions. So in summary, this has been a very successful test. We're able to verify distribution of the colloidal activated carbon. We sustain reductions of both the PFAS and PCE over time. It's anticipated to last for decades. And this is a very low cost alternative to pump and treat. And so bottom line is that colloidal activated carbon provides a flexible, effective in-situ option to address PFAS. We prevent expansion of the problem, and we're managing the risk of PFAS for years to come. With that, I want to thank you, and we'll open it up for questions.
All right, thank you, Ryan. That concludes the formal section of our presentation. And at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple of quick reminders. First, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, after the webinar, you'll receive a link to the recording as soon as it's available. All right, so let's circle back to the questions. First question is a question for Grant. And the question is, some people have said that we can't model PFAS transport. Is that true?
I have heard that. And yeah, there's almost 2 camps where people either believe you can or you cannot model PFAS transport. There is some uncertainty in things like retardation of PFAS at the water table or above the water table or right around NAPL zones where it's more greatly attenuated than you would find if it's just organic carbon. But to be honest, there's enough areas where, like, I don't actually do modeling of PFAS around those areas because it is too uncertain. So I think we can actually model PFAS. There are places where there is uncertainty, we can quantify a range, and if we need to do a sensitivity analysis, we can actually get site-specific empirical data if it's really important to narrow down that range of uncertainty. So I definitely don't believe we should not model PFAS. And I actually find these models, I learn a lot from them, even very simple models, and I find they're very effective even as teaching tools. So I think we should continue to model PFAS transport as long as we qualify the results and where we need to get better data to try and improve the representativeness of those models.
Okay, thanks very much, Grant. So we have another question here. This one is for Ryan, and the question is, what happens when the colloidal activated carbon becomes saturated over time?
Yeah, that's a great question. Kind of back to the longevity, we were predicting that the saturation won't occur for most of the projects that we work on for many years and potentially decades. And so it's something that we have to be aware of and just plan for that on the front end. With that said, if there's an area within a treatment, say a PRB that we've installed, what you can do is either go downgrading of that and then reinstall more PlumeStop, and then you get another decades worth of type of treatment. So it's and really think too that in the future some destructive mechanisms might be able to be paired with PlumeStop as a platform to just kind of maybe regenerate the carbon in situ like we do with other compounds.
Okay, thanks, Ryan. So this is another question for Grant, and it is, how many states have regulations that cover short chain PFAS like PFBA or PFBS?
Yeah, that's not many. So there are federal standards for PFOA and PFAS. Everybody's aware of those. There is actually a federal standard for PFBS, but it's about 400 part per billion, pretty high. There's a few states that will have lower concentration standards for PFBS and PFBA, but for the most part, because they're not long chain, the real focus is on the long chain compounds. That's where the bioaccumulation is going to come from and the risk. So there may be a handful of states with criteria for PFBS, but a lot of those criteria are between 30 and 400 part per billion. So they're and usually we're below those at sites. So I'd say for the most part, they're really not issues across the U.S. There's a few states where they are, and they have to be accounted for. But right now, there's only a few that have that.
Okay, great. Thanks, Grant. So here's another question, and this one's for Ryan. And it is, has PlumeStop been accepted by regulators to treat PFAS?
Yeah, it's a great question. First off, PlumeStop's, it's been around for over 6 years now, and it's been widely accepted for chlorinated solvents and petroleum hydrocarbons. PFAS is a little more newer for that application. But with that said, we've got over 15 sites that have been applied worldwide, with about, I think, 10 or 12 of them here in the United States or North America, and we've got another 4 or 5 planned over the next few months. Every location that we've applied to, or proposed to put PlumeStop in and gone through the regulatory approval process, it has been approved. And so it is widely accepted, and it's gaining more traction with practitioners across the country.
Okay, great. Thank you very much, Ryan. And thank you, Grant. Also, that is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you'd like more information about modeling consulting services for contaminated sites from Pour Water Solutions, please visit pourwater.com. If you need immediate assistance with a remediation solution from Regenesis, please visit regenesis.com. Thank you very much again to Grant Carey and Ryan Moore, and thanks to everyone who could join us. Have a great day.